So good morning, everyone. So I'm really happy to be here today. So today I will present a new method to simulate point process. So my name is Cuong. This is work with Poincaré. He also here there today. So we both come from the neuromode laboratory of Université Côte. And I also work in the laboratory of the Université of Université Côte. And so first, I will say something about point process. So for me, the point process is just a random collection of the points. So I will denote through the talk as xt for the collection of points before time t. Well, and then I will focus only on the point process having the conditional intensity. So that will that is defined through this relation. So you can imagine like it is a probability of having a new point in the small interval giving the path before time t. And more precisely, I will focus in this talk to the Hawk processes and have only self-exciting conditional intensity function. So why we interested in this model? So well, it fits well the model, the data, and also you see at each time you have a spike. The neuron Z emit a spike. It will modify the intensity function of the neuron I via the interaction function at Zi. And well, so somehow it will increase the chain to having a new spike of the neuron I. And well, for the simulation reason here, I will focus on the intensity bounded. So well, that means we will add a delay term, the red term here, to the linear Hawk process. So you can imagine that by adding this term, now you have you will have not no more than 2 points during a small interval during the small delay of delta. So that somehow gives you the idea to have the upper bound of the intensity. So now let's back to the simulation. Well, in the 1980, we have very popular method to simulate the point process. So it's called Ogata algorithm, thinning algorithm. It says that if you have the intensity that is bounded by the positive number m here, so what we do is we just simulate the point, Poisson point process of the intensity m, and then at each point we will decide to accept or reject it with certain probability. And for example, you go to the point t1 and you decide to accept it with the intensity at time t1 and divide by the upper bound m, and go to the time t2. For example, I accept the t1, reject the t2, and accept the t3, and etc. Well, now we need one more ingredient for the new method, and here I would like to introduce the Kalikov decomposition. So while we focus, for example, we consider the linear Hawk process. And let's back one more time to this. So you see that at each time, you need to compute the intensity function. So now, for example, with linear Hawk process, you see that the red term, if you have a complete graph with a huge number of neurons. So this calculates this right term here will be very expensive. So that's why our solution here is we will introduce the random variable z here, and we say that we pick z equal to random to a neuron z with lambda z, and pick mt with lambda mt, and well, we can rewrite the intensity function as follow. And you see the first red term is just the constant, and the second red term is something is just depend on the activity of neuron Z. So well, that's why we denote the first term for phi of mt and the second term for phi of Z. And well, somehow you arrive to the rewrite the intensity as the expectation of something. And well, so the first remark is now instead of you taking all the information all over the neuron, so now you just need to pick a neuron at random. And the second thing to remark here is that, well, you see that you not only can decompose on the neuron, but also in the time interval. So that's why we introduce some, not very new, but the random neighborhood here. So for us, it's the couple of neuron and time interval. So for example, here, it might be one neuron with one interval. And the second might be two different neurons with two different intervals. Or maybe it will pick empty. It means that to decide to accept or reject this point, it does not depend on anything in the past or independent of the past. Well, so we pose a question that, well, in which condition we will obtain to this equation, or we can rewrite the intensity as the expectation of something. So to answer this, so well, trivially, you see that as soon as you can rewrite it as a convex decomposition, or we call it more precisely Kalikov decomposition. So here, lambda is just the polarity distribution over the neighborhood family. And the phi v here I denote for the function that only depend on the neuron inside of the neighborhood v. And well, now we're back to the new method, the simulation method, the new method here, and we call it Ogata-Kalikov algorithm. And well, we keep the first step. We simulate the Poisson point process on each neuron. For example, 3 neurons here. We simulate on it the Poisson process. And then the second step, the new step here, is to each point. Now you will pick a random neighborhood. And then you will decide to accept or reject it, the thinning step. And well, but you see that maybe if you you begin with this point in the first round, so maybe the thinning mark of the 2 points here in the neighborhood of each neighborhood, you don't know the each thinning mark, their thinning mark. So this quantity, this polarity become unknown. So how we solve this problem? So very naturally, you would like to sort it. So somehow you will begin with the point that is minimum in time, and just go until the last point. So you will be sure that you always calculate this quantity, this polarity, phi v over m. Sorry for that. not gamma, but m, the upper bound of the intensity. So the second method we propose here, and you don't know this quality, you will replace it by interval somehow. We will introduce a v-mean we will assume that we will reject all the unknown point in this interval v, and we introduce a v-max by accepting them. So somehow you can introduce p-mean and p-max by v-mean and v-max, and then you have that p will be included in this interval p-mean and p-max that you know, p-mean and p-max. And so you also know that from tuning algorithm, Ogata algorithm, that you will accept a point if you draw a uniform random variable u here. This is less than p. So this means that even you don't know p, the precise value of p, but you still can decide to accept or reject it by this. If u is less than p mean, you will accept, and u greater than p max, you will decide to reject it. And to conclude that we have proposed 2 new algorithms for the hot process, and we even can run it in parallel. And actually, Paul had do it in parallel, and we can do this up to 100 of million neurons in complete graph. And so here is a graph of execution time of the algorithm. And so you see that the Ogata, maybe blue is very bad, even in a million of neurons. It goes very fast to explode. So somehow, and compared to the KO for the Ogata calico, and 2 population, it means that we divide the network by 2 population. And so you see that the Ogata calico decomposition is very better than the classical Ogata algorithm. So we hope to extend our algorithm to the unbounded intensity. That means you don't have the upper bound in advance. And the second remark is we can apply our algorithm in more general point process as soon as you have the calico decomposition. Here are the supervisor. Patricia and Eva is my supervisor, and Alexandre, Patricia is supervisor of Paul. And we would like to thank Curie to support us to come here today. So thank you for your attention.
Thank you. Questions or comments?
Thank you. Can you explain a little more how you split the computation when, you explain your algorithm allows you to use, parallel computation. Can you tell us a little more about the organization?
I think Paul may be more better to answer this question now.
You want to answer?
So, what was the question exactly? It's very basic at the moment. It's just a simple Python package that allows to do multiprocessing. And in fact, the set of neurons is divided as the partition of several population, here 2 and 4. It's because we do computation on a laptop, so there is no point to go more than 4 populations. And I don't know if I can say more. Did I answer the question or? Okay.
Other questions or comments? Yes.
Thank you. You said that you made your computation for Hawk's processes on the complete graph.
Yes.
Can you make also a general graph, and can you do the same Kalikov decomposition for any general graph of interaction?
Yes, for the Kalikov decomposition, we can do it for not in every graph. In fact, yes. I think it depends on how you define the neighborhood family. Is that is this? Yes. So somehow you can do as soon as you can do the Kalikov decomposition, and the answer is you can do it for any type of graph. Yeah.
Thank you. You didn't say anything about the kernel you used, because I guess in the traditional Ogata method will work more or less well depending on how often you have to reject. And that will depend on the kernel you're using. So what kind of kernel have been used? Yeah, the H function.
The condition on the H function, is that? Okay.
I mean, not the absolute condition, but when you compare a traditional Ogata algorithm with the new one you're proposing, I mean, I guess the performance, the gain in performance should depend potentially a lot on the H function you've been using.
Yes, yes, that's true. Yeah. In fact, I think the computation time here is somehow I believe it depends on the choice of lambda, the weight, how you do the decomposition, and also I think I'm not sure to test the other case, but I think it's performed very well in this case, with this particular type of interaction function. But I don't know for the other interaction function, but I'm sure about that the Kalikov decomposition will help us to improve the Ogata classical algorithm. That's what I'm sure. And in particular case with it, here we choose maybe the exponential decay of a function interaction. So somehow I think it performed very well in this case, in our case. Yes.
Okay, other questions or comments? So thank you. And